Good morning, class. Sorry, I'm a couple minutes late today because I got so excited. I finally, I don't know if you guys know this, but, oh geez, how long ago has it been? Um, it was a few years ago, that's about, yeah, a year and a half ago that I wrote a grant with Rachel Halley in the library to get $100,000. It was a $100,000 grant. We won it to install solar panels on the roof of the library. And so this project was finished, installed almost 70 kilowatts of solar panels on the roof of the library, and you can't see them from the ground. It's because the library roof is flat, and it's got that, I don't know what you call it, a parapet, the little wall around the perimeter, so you can't see these solar panels from the ground. But the installation was finished, and the inverter keeps track of how much energy is produced. The inverter is what converts the electrical production on the roof of the library to stuff that DC to AC. And it keeps track of how much energy is produced. And the last piece of this project, which is a very important piece, was that we were going to set up a monitoring site. So this inverter can report data to, it's made by a company called SolarEdge, and it can report data to the SolarEdge monitoring site. And the goal was to be able to create a little kiosk in the lobby of the library. The public reading room, I think, is the goal, where people could come and they could look and they could see how much energy the solar panels have produced since they were created or since they were installed, and how much they're currently producing, and how much they've produced in the last week, the last hour, that sort of thing. And getting that last piece to work was exceedingly difficult for reasons that it shouldn't have been, but it was exceedingly difficult, but I finally succeeded at getting this. I want to show you what this looks like. Let's see. So that's why I was late this morning. I was so excited. I finally got notice that this was working. Okay, so this is what I don't know why it looks like this. It's all weird. Make it full screen. So my screen's really wide, so it's got a lot of, but this is what it'll look like in the library. And you can see right here, this is it doesn't have data for before yesterday afternoon for daily production. I don't know if that data is lost forever or what, but it did keep track of total lifetime production. Almost 170 megawatt hours of electricity was produced by the solar array. So that's so this has been in operation for about 15 months now, maybe 16 months. But the put that in context, my home uses about 10 megawatt hours a year. So this solar arrays have produced enough energy so far to power about 8 to 10 typical American homes for a year. So that's pretty significant. And you can see the environmental benefits. CO2 savings, 165,000 pounds of CO2. That's the equivalent amount of CO2 contained in 1,252 trees. So this is 1 year. And this array has a a service life of at least 20 years, but it might last much longer than that. So if things go well. So this is, when it was put into service, this was the largest solar array in operation by a nonprofit in the whole state of West Virginia. So it was a huge accomplishment, and I was very proud of it, but I was just so sad that we didn't have this kiosk, because it just goes unnoticed. People don't know it's there. And so now hopefully people will know it's there, and they'll be able to see the energy and the environmental benefits of the solar array. I mean, this is the largest renewable energy project on all the Shepherd campus. There's a few other ones that I've been involved with, but this is the biggest one. And it's very significant. All right, so I was excited about that. But let's talk physics. So I want to tell you guys that we will meet for class next Monday. So we got Friday and Monday. I'm going to move the due date for the homework to next Friday, just to give you guys plenty of time to finish it. And we're wrapping things up now. So next week you have class Monday and Tuesday. Tuesday we won't. We might meet. No, I don't think we'll meet on Tuesday for lab. You have just one more class one class Friday, one class Monday, and then after that we got to decide as a group what we want to do. So the week after Thanksgiving is flex time. No exams, no new material served up, but I'd like to use some of that time, or all of that time, to prep you for the final exam, which is the following week. And that means we can do review. The final exam's cumulative, so no new material, but we can do review. We can do practice problems. We can do quantitative practice, conceptual practice. We can do any of that. But I want you to give me a little guidance on what you would want to do, because it's flex time. So let's use it in a flexible way that it has a maximum impact and serves you the best. So let me know what you think we should do that week. Just shoot me an email. If there's specific topics that you want to spend time on to prep you for the final, let me know what that is, what those are, and you know, let's collaborate on forming the agenda for that flex week. All right. The only other thing you'll have that week is to finish up your lab practical exam, which will be that week. All right. Okay, so let's do some more practice problems from the homework. And if you got any questions or comments, put them in the comments. If you got any comments, put them in the comments, and I'll see them. Look at this cutie. She's 9 now. All right, and she's even cuter. Okay, let's see what to talk about first. Oh, I know. All right, so let's talk about a property of rotational inertia that will help you with the homework problems. All right. So let's say you have a situation like, you know, here's an axis of rotation, and you got a couple masses that are all rotating about that axis of rotation. Okay, so things, you know, these masses are rotating around in a circle, and the question is, well, maybe I'll draw this so it's clear that they don't necessarily have the same mass or the same radius. So these lines represent massless little armatures that connect the masses to the axis rotation, but they don't contribute to the dynamics of what's going on. So I'm going to make 2 really small. So 2 small and close, 3 is large and far away. So each of these masses would have a mass, M1, M2, and M3, and each of these masses would have a radius, a distance from the axis of rotation as they're spinning around. And you want to figure out what the rotational inertia of this contraption is. All right, so in physics we oftentimes do approximations, and one place where approximations come up is when there's some sort of physics that depends on the geometry of an object. We make an approximation about the geometry. So these masses are not point masses, but in a situation like this where the masses are small relative to the distance that they are from the axis of rotation, the distances they are from the axis of rotation, you can approximate the masses as a point mass. And it works really well. So that means each of these masses will have a rotational inertia given by the formula for the rotational inertia of a point mass, which is mr squared. So there is, all right, I was going to say something about another problem, but let's keep doing this one and then we'll talk about that. So Holly, I see your question. I'll address that in a minute. So in this case, if you want to find the rotational inertia of the whole thing, a cool property of rotational inertia is you can factor it, because rotational inertia is a sum over all the mass, or an integral over all the mass. You can factor it out like this, so that there's, I don't know if factor is the right word, but there's three terms, I1, I2, and I3. So you can figure out what the rotational inertia is for each of these individual masses and then just add them together. So the total rotational inertia would equal the rotational inertia of mass 1, which is, we're approximating these as point masses, so it's mr squared, plus m2 r2 squared plus m3 r3 squared. Okay. So there's another problem that's assigned, and it involves a situation like this, where there's an axis of rotation. Well, let me move this somewhere else, because this is, go down here. So there's a problem that involves a long rod like this, uniform rod, and it's rotating about a point that's not at the center or the end. So for my problem, the things that you know is this total rod has a mass equal to m, and it's got a total length equal to capital L. So the things that you're given are that this part is some fraction of the total length, and for me it was, I think, a fifth of the total length, and then this part is the rest, which would mean it's 4/5. Okay, so you have this object that's going to rotate about this axis of rotation right here, but it's got a geometry that looks like one thing that we've studied before. Remember, we calculated that the rotational inertia, or moment of inertia, of a long uniform rod rotating about its endpoint was 1/3 ml squared. Its mass times its length squared. But this would seemingly not apply in this situation, because this is for a long rod rotating about its end. Okay, and that's not the situation here. The axis of rotation is not at the end. All right, but you tell me, the strategy that we just looked at of decomposing, maybe that's the better word, decomposing the rotational inertia into individual terms that you add together, factoring is a multiplication term, so that wasn't the right thing to say. But you decompose it into terms that you add together to get the whole. How could you use knowledge about the rotational inertia of a long uniform rod rotating about its end and the specifics of this problem to find the rotational inertia of this long rod rotating about a point somewhere in the middle, closer to one end than the other? What would you do? So while you're thinking about that, put your answer in the comments. I'll answer Holly's question here. So Holly said, will I have a study guide of some sort that covers the entire final exam? And so one thing you will have is the exams, the solutions as well, which are excellent study guides. The gold standard of study guides are the past exams. And but as for something else like an outline, I probably have something that I put together in the past that I can post up. Let me take a look at that. Maybe Holly, you could email me to remind me to look at my resources. I've got a lot of stuff. I'm sure there's something in there that'll be useful, and that would be rad. All right. Does anybody have an idea about this yet? How can we approach this problem with the fact that we know the rotational inertia of a long uniform rod rotating about its endpoint, and we know that rotational inertias of an object can be decomposed into individual terms? What do you think? So look at this object, this red rod, and it's rotating about this point. How could I break that object into multiple pieces, where each of the pieces would could be modeled as an object we already know how to calculate rotational inertia of? Come on. Come on, you guys know this. You really have no idea? I gotta keep talking. Give you some more hints. So, how would you make this red rod, which is rotating about that point, the axis of rotation, how would you make it look? What would you have to do to make it look like a long uniform rod rotating about its endpoint? Or what should I say? Another way I could say this is, if you look at this thing, do you see embedded in this picture a long uniform rod rotating about its endpoint? Do you see it? So this thing is about to start rotating about that axis of rotation. There you go. Yes. Thank you, Holly. Treat them as two separate. So that, how do we apply this idea from up here, where you can decompose an object into individual parts, and there's 3 point masses? How can we apply that idea down here? Well, we can think of this as this is actually 2 long uniform rods. So color one yellow and the other one I'll keep red. So the rotational inertia of this system is going to be the rotational inertia of the red part plus the rotational inertia of the yellow part. So that's going to be, and each of those are long uniform rods. So that's going to be 1/3 the mass of the red part times the length of the red part squared plus 1/3 the mass of the yellow part times its length squared. So now all that remains to do is write these m's and l's in terms of the total length. So we can do that. So the red part is 1/5 of the total mass, and it's 1/5 of the total length. So that part would look like that. And the yellow part is 4/5 of the total mass, and its length is 4/5 the total length. Okay, so you have some algebra to do here. So this is going to be, see, a 1/3 times a 1/5 times a 1/5 squared. So 1/25 ml squared, plus you have a 1/3 times a 4/5 times a 4/5 squared is 16/25 ml squared. So that's going to equal, let's see, oh geez, the numbers. Let's see, 3 times 5 is 15. 15 times 25 is 375. All right. So the red part contributes 1/375th ml squared to the total rotational inertia, and this one's going to be 4 times 16 is 4 times 6. Wait, did I get something wrong here? No, 4 times 16 is 64. Sorry. So you have a common denominator here, and that means the total is 65/375th ml squared, and that would factor, right, you could divide by 5. Numerator and denominator. 65 divided by 5 is 13, and 375 divided by 5 is 75. And here's our answer. Okay, so it's the strategy of decomposing an object into geometries that you know how to calculate rotational inertias of, and then you add them together. So if I were to ask you, I like doing problems like this where, you have like a fan, okay, and maybe it has 4 blades. That's horribly, these are all supposed to look the same. Okay, and I said that this blade has a rotational inertia equal to 2 kg/m squared, and I asked you, well, what is the total rotational inertia of the entire fan then? What would the answer be? So this one has a rotational inertia of 2 kg/m squared. And I said, what's the total? And I know I didn't draw it very well here, but all the blades are the same. All the blades are the same. Thank you, Holly. Holly is out there. Holly is on the ball. I know there's at least 12 of you out there. I don't know where the rest of the class is. But maybe they're going to watch this later. But Holly's being interactive, and she's on the ball. If each one's 2 and you have 4, the total is 8. Okay? Not a trick question. Just a little tricky. All right. So let's talk about the So one of the problems gives you a situation where you're asked to figure out the rotational kinetic energy of a planet. And you're given the specifics about the planet. So maybe your planet is Saturn or Jupiter. So you're given the specifics about the planet, but you're asked it in two different ways. The first part is, a planet rotates about its axis. The Earth rotates once every 24 hours. And so since it's rotating about its axis, it has rotational kinetic energy. And this is a lot of energy. You guys may not know this, but if you've ever heard of the idea of using tidal power to generate electricity, the tides coming in and out. Well, the tides are a consequence of two things. They're a consequence of the moon's gravitational pull being slightly different, because gravity is a function of distance. So if, here's the Earth. Let me look at a little model here. This looks like the Death Star. It's really an eyeball. This is the Earth, and then the moon is out here, and the moon is orbiting, but the moon's gravitational attraction, or I should say the gravitational attraction between the Earth and the moon, is a function of distance. So the moon pulls harder on the near surface of the Earth than the far surface. Right? In other words, there's a gravitational gradient across the Earth, resulting from the gravitational pull of the moon. So it's that difference in force that causes tides. What it does is it causes the ocean to kind of bulge out a little bit because the moon pulls harder on one side of the Earth than the other. And the moon's gravity in absolute terms is a lot weaker than the sun's gravity on the Earth. But the fact that the moon is so much closer than the sun is what creates this tidal force. The fact that there's a gradient, there's a difference in the force from one side to the other. With the sun, not so much because it's so far away. So the sun doesn't cause the tides, the moon causes the tides. So that's one factor. The other factor is the Earth is rotating. So as the Earth rotates, the surface of the Earth, or the bottom of the ocean, rotates underneath these areas of the ocean where it's bulging out due to the moon. And so that roughly, it's not universal, but most places on the Earth's surface coastal areas have 2 high tides and 2 low tides every day, diurnal tides, and that's a consequence of the Earth rotating under these bulges on either end and these troughs in the middle. So tidal power. So there's a long story. It's a long story, but the point I want to get to is tidal power takes advantage of these tidal changes. And whenever you harvest tidal energy, what you're really harvesting is some of the Earth's rotational kinetic energy. And the sloshing around of the oceans creates friction that is very gradually slowing the rate of rotation of the Earth. And so we are, the oceans are slowly converting the rotational kinetic energy of the Earth into thermal energy from the friction of them sloshing around. But it's a tremendous amount of energy. It's not going to be eliminated anytime soon. But I gave you this problem where you calculate the rotational kinetic energy of a planet about its axis, and then the second part is the rotational kinetic energy of the planet as it rotates the sun. So for the first part, what geometry is a planet. When it's rotating about its central axis, it's a sphere. So I closed my web browser. Let me open it again. Let's try this. Okay. All right, so yeah, my planet was Saturn. All right, so you can click this link here, and it takes you to the pertinent section in the textbook, and there's a table in here. Here it is, that gives the rotational inertias of a bunch of uniform geometries. So here's the rotational inertia of a disk or a cylinder rotating about its central axis. Rotational inertia of a hoop. So we derived those last time. So here's a sphere, a solid sphere, that's a planet, rotating about any diameter, so a central axis. 2/5 mr squared. 2/5 mr squared. Okay, so when I'm trying to figure out the rotational kinetic energy of Saturn, I'm given its mass, I'm given its diameter. Be careful, divide by 2 to get its radius, and also convert the meters. It's in kilometers, convert to from kilometers to meters. All right, and then I can calculate the rotational inertia of Saturn about its central axis. Okay, and but what about the second part here? It says the orbit around the sun. They give you the distance, so that's its rotational distance. And in this case, the axis of rotation is the sun. It's rotating about the sun. So in that case, it's like I was talking about earlier. You have a situation where Saturn is enormous. It's one of the largest planets in our solar system. It's the second largest planet in our solar system. And so it's definitely not, strictly speaking, a point mass. But if we want to study how Saturn rotates about the sun, I mean, look at the differences here. So Saturn has a diameter of 10 to the 5th, approximately 10 to the 5th kilometers, but its orbital radius is 10 to the 9th. So the difference between those two scales is 10 to the 4th, which is 10,000. Okay, so what I'm saying is the distance from Saturn to the Sun is 10,000 times greater than the distance across Saturn. So from the Sun's perspective, the perspective of the system, it seems reasonable to approximate Saturn as a point mass. So its rotational inertia about the Sun is the rotational inertia of a point mass, mr squared. Mr squared. So for the first part, you use the formula for a sphere, 2/5 mr squared, to calculate rotational inertia. For the second part, you use the equation for a point mass, mr squared. All right, so one more thing about this problem. Here, let's go to the whiteboard here. So rotational kinetic energy is 1/2 I omega squared. So we just talked about how you calculate I. For part A, it's 2/5 mr squared. And for part B, it's just m r squared, but the r's are different. Here the r is the radius of the planet, because it's rotating about its axis, and here the r is the orbital radius for part B. All right. But what about omega? This is angular speed, and the units we want to use are units of radians per second. But if we look at the problem here, let's just look at the second part. So it says the period, it takes 10,800 days. Whew, it's a lot of time for Saturn to rotate once around the Sun. So for part B, the orbital, the rotational speed, the angular speed, is 1 revolution every 10,800 days. All right, but I got to convert that to radians per second. So how do I do that? Well, 1 revolution around the Sun is, in angular units, is 2 pi radians. All right, so that will get rid of the revolutions. And now I got to get seconds instead of days. Well, all right, so 1 day is 24 hours. So that'll get rid of the days. And 1 hour is 3,600 seconds. So that'll get rid of the hours. When I do that multiplication, see, it's 1 over 10,800 times 2 pi over 1 times 1 over 24 times 1 over 3,600. I'll have units of radians per second. So whatever that is the value that will go in for omega in part 2. All right, so you got some unit conversions to handle with this problem. Okay. So I think that discussion that we just had is enough actually to get you through the entire problem set. There's a couple problems on torque that are we'll talk a little on Friday about. We'll talk Friday about torque in some more detail. But torque is there's 2 ways to think about torque. So torque is, there's like this this rotational version of Newton's second law. Instead of F equals ma, and actually it would be net torque, total torque equals, instead of net force equals, well, let's write it out. This is Newton's second law. Net force equals mass times acceleration, and those are vectors. Net torque equals rotational inertia times angular acceleration. So that's one way you can think about torque. Another way to think about torque is this cross product between a force and a distance, which is also RF sine theta. And that's, if you have an axis rotation and you exert a force right there, and it's a distance r from the axis of rotation right there, and the angle between them is theta. There's an angle between them. There's 2 ways to calculate it. So if the problem says the force is exerted perpendicularly, that's telling you that the angle between the r vector and the force vector is 90 degrees, and the sine of 90 degrees is 1. So that's when, how do you generate the most torque? Exert a force perpendicular to that line that goes along from the axis of rotation to where the force is applied. All right, so let's wrap it there today, and we'll talk some about torque on Friday. Now, the last problem, well, the second to last problem. The last problem is a lot of fun. It's a video of it's one of those video vignettes of an experiment which involves shooting a bullet into a block of wood. And what they do is they shoot the bullet into the block of wood right in the middle, and the wood goes straight up. But if the bullet hits the wood not exactly in the middle, not exactly in the center of mass, what happens is the block, not only does it start to go up, it gains energy, translational kinetic energy from this collision, it also starts to rotate. So it gets rotational kinetic energy too. And I actually got to see the people who developed this experiment gave a presentation on it at a physics conference I went to a few years ago. Back before COVID, when we could actually meet with people in person, and it was really interesting. So this video vignette is a lot of fun. But the problem before that is, here, let me show it to you. This is it's this one, where you have one mass pulling this pulley one direction, exerting a torque in one direction. So this weight pulls in one direction, this weight pulls in the other direction at a different radius. So you have two torques that oppose one another, and the net torque determines the angular acceleration. If we scroll down here, you'll see I got this problem wrong. And I suspect, alright, so, I get problems wrong too. So maybe I made a math error, but I checked it and I didn't find the math error. So what I want you guys to do is attempt this problem, maybe after Friday. We'll talk more about torque on Friday. And let me know if you are getting it marked wrong too, because I am suspecting that, it's probably something I did, but it might be something wrong with the problem itself, the way it's coded in WebAssign. And in which case, this happens every once in a while still, and I gotta know that so that I don't count it against you guys. Alright? So I'll keep an eye on that, and you let me know if you get it wrong too. Alright, gang, so that's it for today. I will see you on Friday, and keep on working hard. Alright? Almost to the end of the semester. Oh, the problem is worth 0. I wonder if it's so funny. Oh yeah, okay. It's worth 0 points. So that tells, you know what that tells me? It tells me that I ran into this before and assigned the same problem before, and decided to make it worth 0 points because it's not coded right. And it also tells me that I completely forgot. And so I did the same thing again and discovered that it's coded wrong. Oh my gosh. So I totally forgot about that. But it's worth 0 points, so it won't count against you if you get it wrong. But I'll leave it in there so you can attempt it. It's a good problem. And maybe I'll do a video. I'll do a video tutorial on this problem and post it up so you can see how, one right answer. All right, gang. I'll see you Friday. Have a great day. Bye-bye.